1 million seconds is about 11 and a half days. 1 billion seconds is almost 32 years. The two numbers look nearly identical on a screen. A 1, a word, and a different first letter. Yet the gap between them is enormous. Most people know that a billion is 1,000 millions. Knowing it and feeling it are different jobs, and the human brain is much better at the first one. Put 3 coins on a table, and you know there are 3 almost instantly. You do not count 1, 2, 3. Your visual system simply registers the amount. Researchers call this subitizing, and it usually works for only about 3 or 4 objects. Add 15 more coins, scatter them around, and the experience changes. Now you must count, group them, or make a rough estimate. That small number skill is ancient and useful. An animal deciding whether to approach 2 rivals or 6 does not need written arithmetic. A person gathering food needs to notice that one basket contains more fruit than another. For quantities beyond a few items, humans and many other animals rely on an approximate number system. It gives us a sense of more, less, and roughly how much, without producing an exact total. The approximation follows ratios more naturally than absolute differences. Telling 8 dots from 16 is easy because one group is twice as large. Telling 80 dots from 88 is much harder, even though the difference is still 8. Adult performance in these tasks often depends on the ratio between the sets. The larger the quantities become, the wider the brain's fuzzy estimate tends to be. A pile of 12 apples and a pile of 24 apples feel clearly different. A crowd of 1,012 people and a crowd of 1,024 people do not. Mathematically, both pairs differ by 12. Perceptually, the second difference is almost invisible. This ratio-based behavior is related to Weber's law, a pattern found in many senses. We notice relative change better than fixed change. 1 extra candle in a dark room matters. 1 extra ceiling light in a stadium probably does not. Written numerals let us escape some of that fuzziness. The symbol 847,293 can represent an exact quantity, even when nobody could look at 847,293 objects and recognize the total. But the symbol is a cultural tool. The brain has to connect marks and number words to magnitude through years of learning. That connection is strong for familiar scales, prices, ages, distances, scores. It becomes weaker when the scale leaves ordinary life. Take a blank line with 0 at one end and 1 billion at the other. Where should 1 million go? The correct answer is 1,000th of the way across, so close to 0 that it would nearly touch the endpoint. Many people place it much farther to the right. 1 million feels like a major number, and it is, but major is not a position on a linear scale. Experiments on number line estimation show that people's judgments can become strongly compressed when ranges are huge. In one study using endpoints from 1 to 10 to the 16th power, participants showed large compression effects. Other experiments found that the range and the distribution of examples changed how people place the same numbers. So the mental number line is not a fixed ruler stored in the head. It is rebuilt from context, landmarks, and whatever values happen to be nearby. That explains a common news problem. A city project costs $40 million. A national program costs $40 billion. Both may be described as massive, and both may appear beside photographs of cranes, politicians, or unfinished concrete. The words generate roughly the same emotional weight. The second amount is 1,000 times larger. Add 3 zeros and the visual change is tiny. Commas help, but only if you pause to read them. On a phone screen, 12 million and 12,000 billion share most of their digits. The eye catches the 12. The mind catches a lot. The keyboard is still clicking, the article keeps scrolling, and the 1,000-fold difference can slide past unnoticed. Working memory does not help much here. It can actively hold only a small number of chunks at once, with classic reviews often placing the central capacity around 3 to 5 chunks under controlled conditions. A large quantity may require several linked pieces: the number itself, its unit, the relevant population, the time period, and the comparison value. Drop one piece, and the number changes meaning. 500,000 cases sounds serious. 500,000 out of what? A million people would mean 1/2. A billion people would mean 1/20th of 1%. The numerator is identical, but the risk is not. People often focus on the count that is easiest to picture and underweight the denominator. Researchers call this denominator neglect or ratio bias, depending on the task. A jar with 9 red candies out of 100 can feel more attractive than a jar with 1 red candy out of 10, because 9 winning candies look better than 1. Yet 9% is lower than 10%. The larger numerator pulls attention away from the larger denominator. Not always, of course. People can calculate the answer. The bias appears when intuition speaks first and careful comparison arrives late, or never arrives. Education improves numerical reasoning, but it does not turn the approximate system into a perfect measuring instrument. A study of more than 5,000 highly educated participants found that numeracy predicted better performance on financial, medical, probability, and denominator neglect tasks. More numerate people tended to deliberate more and judge their own confidence more accurately. Even among educated adults, the advantage was not simply knowing more math. It also involved noticing when the first answer deserved a second look. Now place 30 grains of rice on a plate, then try to picture 30,000. The natural move is to imagine a larger pile, not 1,000 separate groups of 30. At 30 million, the image barely changes. Our visual imagination runs out of resolution. We reuse the same mental picture and attach a larger label to it. Exponential growth is even worse. Suppose something doubles each day. 1, 2, 4, 8, 16. Early steps look harmless. After 10 doublings, the starting amount has been multiplied by 1,024. After 20, it is more than 1,000,000 times larger. People routinely underestimate exponential trajectories and can remain confident in those estimates. This matters for compound interest, epidemics, computing capacity, population growth, and debt. The problem shows up in a boring spreadsheet too. A value growing by 7% each year does not add the same amount annually. The increase itself grows. Drag the formula down 20 rows and the final cell can look wrong, even when it is correct. Linear intuition expects a staircase. Compounding produces a curve. Large numbers also lose emotional force. One damaged house is a place, a kitchen, a wet mattress, a child's toy under plaster dust. 10,000 damaged houses are a statistic. The mind cannot build 10,000 detailed scenes at once, so it compresses them into a category. This does not mean people stop caring. It means attention and imagination have limits, and those limits can make very different scales feel strangely similar. There are ways to fight back. First, translate unfamiliar quantities into familiar units. A billion seconds becomes nearly 32 years. A trillion seconds becomes more than 31,000 years. A budget can be divided per person, per household, or per day. Data storage can be converted into hours of video. Distance can become travel time. The conversion is not perfect, but it gives the number somewhere to land. Second, compare ratios before totals. Ask, compared with what? A $2 million overrun may be disastrous on a $3 million project and almost invisible on a $200 billion program. A disease affecting 10,000 people may be common in one population and rare in another. Keep the denominator beside the numerator. Do not leave it 3 paragraphs earlier. Third, build landmarks. 1,000 is 10 hundreds. 1 million is 1,000 thousands. 1 billion is 1,000 millions. Put those relationships on a line or in a simple table. The point is not to memorize more zeros. It is to stop treating million, billion, and trillion as 3 neighboring words meaning very large. Physical comparisons help, but they need discipline. Stacking 1,000,000 banknotes and stacking 1 billion banknotes can make the difference vivid, provided the note thickness and assumptions are stated. Otherwise, the comparison becomes another impressive claim floating without a scale. A neat animation can mislead just as easily as a bad headline. And yes, this gets messy fast. Units change. Inflation changes money. Populations differ. A number can be exact, while the estimate behind it is uncertain. Sometimes the most honest representation is a range, not a dramatic single figure. Good numerical thinking includes knowing what the number does not tell you. Our brains are not defective calculators. They were built to make fast decisions with limited information, using small, exact sets, rough magnitudes, ratios, and familiar landmarks. Written mathematics extends that system far beyond its natural comfort zone. It lets us describe national budgets, geological time, galaxies, and microscopic probabilities. But the symbols can travel farther than intuition can follow. So when a huge number appears, the useful question is not only, can I read it? Ask whether you can place it on a scale, compare it with something meaningful, and keep its unit and denominator attached. 1 billion is easy to say. Understanding it takes work. That small pause between reading a number and trusting your feeling about it may be the most important calculation of all.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!